But I'm still like.
All right. Shall we get started? Let me look up a file real quick. Let me find this file. All right, we're beginning. Well, no, we still have 30 seconds. Yes, we got it, Thank you. Yeah, everyone gets a 10-point bonus. I'm just kidding. No. All right, so last class we were talking about surface areas, right? So the idea behind the surface area was that we basically took the arc length formula that we had learned prior to that and just really did a slight little tweak on it. So let's just recall those formulas before we move on. If you have some curve, some y equals some function of x, and you want to know the length of that on the interval a, b, it is what? Integral a to b, square root 1 plus f prime of x, that thing, squared dx. And we talked a little bit about how you could do this if the curve was a function of y instead of x, but really I want you to be able to do something like that, okay? Find the length of that curve. So we did that, and then we said, all right, well, what if you take that curve and instead of finding the length of it, you take that and you wrap it around the x-axis, right? And then look at that surface that it creates. And then we try and find the surface area. So if we wrap that around the x-axis, it's going to look something like this. Okay, but remember, this is just the surface. So I can put my hand through here, right? And we're trying to find the surface area of that. All that is basically that. I'm going to put a. It's that integral with a 2 pi out front, integral a to b. And then there's one more thing. The function itself is outside the root. And then we have the root of 1 plus f prime of x, that thing squared again, dx. Right, so just adding your 2 pi, just add a 2 pi and f of x right here, and you've got the surface area formula. Like when we were doing volumes, right, we had two methods for volumes. We had washers and we had shells, right? And then like the quiz I gave you a region. I had you wrap it around all these different axes, yes? On this surface area, I'm just wrapping around the x-axis, yes? But we could do it at different lines. We're not going to do that, all right? We could try and find the surface area wrapping around the x-axis or y-axis or some line up here, down here, over here, over here. For surface area, I just want you to be able to do this one basic one, which is just around the x-axis, and that's the formula for it, all right? Good. Just be aware that we could head down that road, but we don't have time to go down that road. All right? Okay, so I'm thinking that maybe your quiz on Monday would just be like a problem where you have to set up these integrals. You know, just set that up, maybe 5-10 minutes in class at the beginning and be done. All right? So. Okay, now I had unintentionally skipped something when we were doing volumes, but I said it was okay because it's such a different topic. It's the same, but it's not like we missed anything. So let's cover that, and then after that, I don't know if we're going to do applications or if we're going to jump into Chapter 8. My gut says let's go to Chapter 8 because that's what's on the schedule for today, but we might do applications. We'll see. All right, so I'm going to put this problem up here first in words, all right? And maybe I'll type it. I don't know. No, I'll just write it. Okay, so just let me write it first and then we'll talk about it. A solid has a base which is the region bounded by y equals x squared minus 1 and y equals 1 minus x squared. Oh, shit. Hurt myself here. Pardon?
There's a chair there.
Yes, there is. Okay, a solid has a base which is the region bounded by those two curves. All right? Now here's the weird part. Cross sections of this solid which are perpendicular to the x-axis form squares. Find the volume of this solid. Okay. There we go. All right, so we have this solid object, all right? Don't be thinking about rotating things around axes anymore, okay? Just, we have this solid, and I'm trying to describe to you what the solid looks like. First of all, the solid has as its base, so if I set it onto the table, the base, right, of this solid is the region bounded by those two curves. So let me draw that first. I have y equals x squared minus 1. Not very good. And then I have y equals 1 minus x squared, like that. Okay, so the region right there between those two is what the base of this solid looks like on the ground. Okay? So if I were to set it down, that's what it would look like on the ground. Make sense? Okay, now it says, if you were to take this solid, so imagine I've set this on the ground, all right? And I've got it on the ground, so imagine turning that over, right? Well, I come in here with a knife, and I cut through this solid. Okay, so we're looking from the top down. And I cut through with a knife that is perpendicular to the x-axis. So my knife is going to be like this, right? Not like this. My knife would be perpendicular to the y-axis. But if I cut it like this, then my knife is cutting through that solid, right? Perpendicular to the x-axis. And what I'm going to tell you is that when I cut through the solid and kind of look at it from the side, like a cross section, what I see is a square. All right? And that would be for every slice I make. Everyone's got this look like, what? What? Okay, you should be looking like that. That should be a little confusing, all right? So I have a visual to help us see this, but this is kind of, without any computers, this is what we've got, okay? So I'm going to try right now to continue to do this without a computer by trying to draw this three-dimensionally. So when we draw things three-dimensionally, what I suggest you do is draw a vertical line and then draw an X, but make it like a squashed down X. Like this. See how that X looks kind of squashed? Don't do it like this. People will do like that. It's really hard to draw three-dimensionally if you draw like that. Squash that X down. Y'all see it? Okay, so what I want us to see now is that all this is this kind of laying down on the ground. And this axis right here is our X, and this is our Y. Can y'all see that's kind of the ground? Yeah? And so my parabola things in here look like this now. Now, this might be hard for you to draw, but can you all see that region on the ground? Well, I'm not happy with that. I want to bring this over a little. Okay, do you all see that? Does that look like that laying on the ground? Okay. So if I were to imagine this solid that's kind of above this, right? When I do these cross sections, so if I come in here, let's say I cut through this solid straight down with a knife and it cuts through like that. Over here on this picture, that would be like from here to here, right? Something like that. Y'all agree? And when I look at that, if I were to kind of like take that piece off the side and look at it from the side, it would look like a square. So if I were to look at this from the side, it should look like a square from the side. Do y'all see that? Kinda? Okay. Again, I'm going to show you this on a computer, but we have to act like we don't have a computer for just now. All right, let me cut through with a different knife. Okay, or same knife, sorry, same knife. Different cut. So what if I cut it here? Right? Over here in this picture, that's going to be further back, right? Like kind of like along here. And what can you tell me about that cross section? It's a square, right? But that square is actually going to be bigger, right? Taller and wider than the blue square was. So I've got a tall square here, like that. All right? Let me do another cut. I'll do a red cut, even though I have red here. This red cut, I'm going to get real close to the edge here. Right there, I'm going to make a cut right through there. Which over here would be something like this, right? And what about that square? Small, right? Because if it's a square, all sides have to be the same, and the red side is the length of the side, so you get a small square. Something's going on here.
I had the cop yesterday.
What's that?
I had the same cop.
You did? So it's your fault.
I think it comes from
Is that what you're saying? It comes from math. All right, so this is the solid we have. Imagine all the cuts, right, would form something, and we want the volume of that. Make sense? Okay, now let me use the computer to help us see this. Code looks blurry. Okay. All right, I'm going to erase the problem so we can see it up here. All right, so there it is. Let me get to squares here. Okay, and
Oh, that's cool.
okay, so let me tilt this. So if we're looking at it from two-dimensional, right, two-dimensional, there's our knife cutting through. But every time we make a cut, we look at it from the side and we see squares. So as we move that cut through, squares are real small over here, right? And they get bigger, and then they go through. When we get to there, they start to get smaller along the other side. Okay? So what does this solid look like? Like that. That's what it is. So see all my squares in there? If I were to put all those squares together, I would get that green thing. And so what we want to know is what is the volume of that solid. Make sense? Does that seem difficult or does that seem hard? Well, what's the power of the integral? Power of the integral is that it adds up an infinite number of things for us, right? So just like we did before when we took a region and wrapped it around the x-axis, didn't we always go to the side and say, let's just find a formula for that one little washer or that one little shell? If we can find a formula for that one little shell, then we can just add those all up. So what we want to do is imagine coming in here and taking like this really, really thin slice, right, that has a little bit of width to it, okay, and taking it and taking a look over on this side, you know, what that is and find a formula for its volume, and then we just add them up, okay? So I'm going to draw the 2D picture up here again, just so we have it. Okay, so if I come in here with my knife and I do this infinitesimally thin slice, that's kind of like we had with the rectangle from before, isn't it? Right? That right there is this infinitesimally thin slice that we're going to take. Let's look at that three-dimensionally. Three-dimensionally, right? Three-dimensionally, that's what that slice would look like because it's a square. You'll agree? Okay. Yes, thank you. Thank you. Someone's finally answered me today. All I've had is nods all day. Thank you. All right. So this is just a little box, really. We know the volume of a box is length times width times height, right? So we need to figure out what the length, what the width, what the height is, right? So what do you want to start with? How wide is it? How about the thickness of this? What do y'all think that is? dx, right? So what we're starting to see here is that what we're going to do is we're going to do these slices all the way through, right? So we're going to start out over here and slice our way through this thing. So the dx is the width, right? Okay, so that's dx. All right. How long is that side? Yeah, that's just the height of this, right? Which is your top function minus your bottom function. And we know what those are, right? Which one is the top one? The top function is 1 minus x squared, and then minus the bottom function, which is x squared minus 1. Right? Now, some of you might be concerned about the fact that the bottom function is down below the x-axis. It's not going to be a problem because when you subtract the negative, it would become positive, so it accounts for it as a distance. So this works, okay?
I have a question.
Yes.
In the original graph you put on the board, the top function was x squared minus 1.
You sure?
Yeah.
Did I label it wrong? No? I don't know.
Okay. I guess I just wrote it down wrong.
Yeah, maybe, because they were right next to each other, maybe you just flipped them. All right, so this top one, this one right here is x squared minus 1, and the one that comes down is the 1 minus x squared.
Oh.
Did I? Oh, yeah. Yeah, it looks weird because that one's on the bottom, but yeah, this one goes with that one, and this one goes with that one. Parabola opens up or down, positive in front, negative in front, right? Okay, y'all agree that's how wide this thing is? And it's a square, right? So the height is the same as the width. So I know that this side's the same. So this is also 1 minus x squared minus x squared minus 1, right? And let's just clean that up because this does simplify. What is that? Is that just 2 minus 2x squared? Right? That's what that is. Just drop the parentheses, put them together. That's what this is. 2 minus 2x squared, right? So this, what we've done is we've taken the geometric picture and we've said, okay, we're going to come up with a formula for the volume of one slice, right? So the volume of just that slice, what would it be? The volume of just this slice would be this, right? Times dx. So I'm just going to put 2 minus 2x squared dx. And that's the volume of a single slice. I want all the slices, right? So I'm going to now bring in the integral. And my integral needs limits of integration. What are my limits of integration going to be? Well, x is the variable, right? And x is basically our left and right as we slice through. So we need to know where we start and where we stop, and those are the intersection points of those two curves, which you could find algebraically, or just by inspection, it's 1, right? 1 and negative 1. So I can go negative 1 to 1, and then I've got 2 minus 2x squared, that quantity squared, dx. There it is. That integral, whatever its value is, right? Whatever the value of that definite integral is, represents the volume of this solid. Make sense? And you can do that with any solid you want. As long as someone describes to you what the base is and what the cross sections look like, we can come up with a formula. So this, I think this topic really illustrates the power of the integral, that it's not just like, you're not just using it to do volume solids, right? Like revolving. It's not just that. It's any time you need to add up a bunch of things forever, and you can always bring out the integral. All right, so let's change the problem. I want to do the exact same problem that we just did, okay? Same base, but this time I would like the cross sections to be semicircles. Okay? Semicircles instead of squares. Now when I say a semicircle, I mean a half circle, right? Half circle. So I don't want to write the whole problem down again, right? Just change squares to semicircles. So if I do semicircles, then I still have this same picture of the two curves, right? I'm still going to do a slice, this infinitesimally thin slice. But now when I draw that slice over here, it needs to be a semicircle with some thickness to it, right? So I'm going to draw it this way. Good enough? See, that's my little semicircle that has some thickness to it. And we need the volume of this. Well, the width we know, right? The width is just dx. That's not going to change. But to find the volume, what am I going to need on this thing now? I know how wide it is. Yeah, I need to know the area of that half circle, don't I? If I know the area of this semicircle, multiplying it times the width would give us the volume. So we just need right now the formula that gives us the area of that semicircle, right? So I'd like to know that distance because that's the radius, right? And we know that the area of a circle is pi r squared. But we actually only want half the circle, don't we? So we know the area of this front face right there is going to be half of pi r squared. But what's the radius for us? What's the radius? It's half of the distance between these two, right? It's half of the distance between these two. Now, this problem is symmetric, like the top and bottom are the same, but they don't always have to be. So you always want to look at the distance between these two and take half of that distance. Do you understand what I'm saying? Like if this parabola was here, but then there was maybe a line coming through here, you couldn't just take the top half. You have to do the whole distance divided by 2. So my radius is what? It's half of the f minus g again, which we already know is 2 minus 2x squared, right? We did that from the previous problem. We know that the top minus the bottom is 2 minus 2x squared, but we're doing half of that. Yeah? So the area of this thing, the area of this would be half of pi times that radius, which is half of, I'm running out of room. Let me do it over here. I'll do it up here. So this is half of pi times half of 2 minus 2x squared, all of that squared. Do y'all agree? 1/2 pi. This is my radius, right? You said that's the radius, and then that radius squared. Now to make my life easier, what I'm going to do is out of this right here, I'm going to pull a 2 out, pull that 2 out and cancel with the half. Right? So if I pull the 2 out and cancel with the half, I get 1/2 pi, and then the 2's in the half canceled, so all I'm left with is the 1 minus x squared squared. Y'all follow that? So now I have a formula for the area of that front face. and then I have the width. So the volume would be those two multiplied, right? And if we want to add them all up, we bring in the integral. So the volume of this should be the integral from -1 to 1 again. This time we have some constants in play, don't we? We have 1/2 pi, right? So I'm just going to, I'll leave it inside the integral. You can pull that out. 1/2 pi, and then you have the 1 minus x squared, that quantity squared dx. Area times the depth or thickness of the slice, integral from -1 to 1. Not quite sure the looks y'all are giving me if this is like, yeah, we got it, no problem, this is cool. Or if this is like, what the, you know?
It makes sense.
Okay, so you want to see them? See what they look like. So if we do semicircles, that's not a semicircle. What the hell? There they are. I must have this wrong in my code. What the heck? Okay, it's okay. All right, so if you were to compute that integral, you would have this. So here was our region, right? Here is our semicircles. They get smaller towards the tip. They get bigger in the middle, right? All of them together, you get this shape. It's going to look hollow. Just ignore the fact that it's hollow. It's really solid, right? There it is, okay? So we'll do one more. This time we'll cut it and we'll have equilateral triangles. So I've done squares, I've done semicircles. How would the problem change if we do circles instead of semicircles?
Take the 1/2.
Yeah, we'd never do that 1/2, right? We would just take that out. Okay, so let's do nothing. There's nothing. Yeah, so let's do equilateral triangles. I believe this is not it. Let me look. Yeah, that's not an equilateral triangle. But it's okay. It's close enough. Close enough. Well, maybe it is. Kind of looks like an equilateral triangle. All right. So we'll go with equilateral triangles. When we put them all together, we get this shape. And that's obviously different than the other two we've done, right? That's going to have a different volume. All right. What is an equilateral triangle? All sides the same length, right? So doing an equilateral triangle, I'm going to be real lazy here, equilateral triangle. Then when we have our 2D picture, like this, and we do that little infinitesimal slice, like that, when we lay that down on the ground, look at it kind of three-dimensionally, we get something like this. And we know how wide it is, it's dx. We, again, need to figure out a formula for the area of this. And what do we know? I mean, what part of the triangle do we know? The base, right? We know this distance. And that, we've done it several times now. This is 2 minus 2x squared, right? That's what that is. So now this is a good question. What is the area of this triangle? 1/2 base times height? Yeah? Y'all agree? So there's a better formula. So I'm going to take you back to pre-cal for a moment. This may have come up in Cal 1. You may have seen this, but the standard formula for the area of a triangle is 1/2 base times height. That's the standard formula. Everyone kind of knows that. But the thing is, in order to use that formula, you must know both the base and the height. Here we know the base, but we don't know how tall that is. Now we could algebraically go and try and figure it out, and we could get it, all right? But it's just going to take us a little bit of time. You just like drop, you take your equilateral, you drop, and so you know the distance from here to here is 2 minus 2x squared. So the distance from here to here is half of that. And then you know the hypotenuse is also 2 minus 2x squared. So you know this side, and then you can solve for that side. Like Pythagorean. But it's too much work. It's better if you know this other formula. Does anyone know the other formula? AB sine theta, there it is. Okay, so in this picture, if we label this side right here, from here to here, if we label that A, and we label the angle between those theta, there is a formula from pre-cal that says that the area of this is 1/2 AB sine theta. And that was on your formula sheet, yes? This formula is really, really nice if you know the angle between the sides. But the fact that an equilateral triangle has the same length sides, that means all angles are congruent, so they're all 60, right? So you know that the angle in there is 60 degrees or pi over 3. And so it becomes very easy to use this formula. So this formula you use if you know the base and the height. This formula you use if you know two sides and the angle between those two sides. We know the angle between the two sides and we know the two sides, right? We know these lengths. They're all the same. Now, let's just look real quick and see where this formula comes from. It's not magic. It's actually pretty simple if you just do something real quick. Look at this triangle right here. And I want you to see, look at that right triangle right there. Okay? That red one? What is sine of theta according to the definition of sine in right triangles? Sine of theta according to that red picture would be opposite over hypotenuse, right? So it'd be h over a, right? Okay. I'd like for you to solve that for h. So solve this for h. What would you get? A sine theta. Okay. So now take this formula here and replace that with a sine theta, and you get that formula. Right? That's all it is. There's nothing else magical about it. Pretty simple? All right. So my advice to you going forward is to always know that this formula exists, because it's very useful in cases like this where you have like equilateral triangles. So now, getting back to this, I wanted to know the area of this little piece, right? The area of that should be 1/2 a times b, right? A and b for us are the same thing, right? So this is also 2 minus 2x squared. So what should I put? 2 minus 2x squared squared, right? Because it's times itself. So that's your 1/2 AB. And then sine of 60 degrees, sine of pi over 3, right? Which is root 3 over 2. Again from pre-cal. Root 3 over 2. And if I just clean that up a little bit, I'll get root 3 over 4. 2 minus 2x squared squared. That is going to give me the area of that little front face. And then I multiply it times the width, and that gives me the volume of that little slice. And then I use the integral and I add them all up. So the volume of this would be integral negative 1 to 1 of root 3 over 4, 2 minus 2x squared, that quantity squared dx. There we are. What do you think? Yeah, see how it goes. I mean, there's a few problems. I don't have my book, man. I don't have my book, but I think there's at least a problem. If for some reason you don't see in the homework a problem like this, just go look through the section on volumes, which is 7.2. And in the back section, just look for a problem where it says, that look like this. But make sure it's talking about slices that are perpendicular to the x-axis. Because you can also slice perpendicular to the y-axis, which I haven't talked about, but you could do a similar sort of approach. Okay? That was it. On the 7.2, I think it was, right? Yeah. So, okay. All right. That's it for cross-section volumes. All right, so I'm going to let you all decide. One of the very few times you have control in this classroom. I have two options right now. I can I can do an application of integrals where we talk about, there's one section with applications. I can talk about center of mass, moment of inertia. It would just be showing you how we have formulas that can calculate these things, and we won't really get into any like computing them all the way. We'll just set them up, probably use Wolfram Alpha to do the calculations. Or we can move into Chapter 8 and start out with sequences. So what do y'all want? Do y'all want to do applications or sequences? Application? Application? Okay. Sequences? That's a tough one.
What would help us better?
Sequences. Yeah, the more you see of Chapter 8, the better. The more you see. Now, if at the end I have some time, I can throw in, see, the thing is at this point, is like when you get to another class where you have to do integration, most of the time they're going to hand you a formula that works for that specific scenario. You know, like in a physics class, you might be asked to calculate the flux of something, or they just give you like the formula, and it's an integral, and you can do it. It's kind of like, it's like the formula that we did a second ago where we were, with washers, where we said it was always going to be like outer radius squared minus inner radius squared, and then times pi, and all that. Like they give you some formula, and then you have to actually execute the math. All right, this class is more about executing the math than it is about like, hey, look, we can use this for centers of mass, or we can use this for hydrostatic pressure, or we can use this for all these different things. Like that gets, you get more in detail in that when you're in specific courses that are geared towards that. Does that make sense? This is still a math class, not a application of math class. But if I have chance at the end, I will take a look at it. I think you can say that, you know, volumes, wrapping stuff, that doesn't seem very practical in the real world maybe, I don't know. But again, the whole point is that you understand that the integral, the definite integral, is a way of doing summations of an infinite number of things that you could not do without the integral, right? You can't do it. All right, we're going to do Chapter 8 then. Chapter 8 starts out kind of fun. And then, no, it's fun the whole way. It's fun the whole way.
Starts out fun. Sounds like a horror movie.
The problem with Chapter 8 is most of the time people have not seen this. All right, so it's like a brand new thing, and then it just gets really, really heavy. All right, so Chapter 8, series. Series is the name of the chapter. Okay, and we're going to start out with 8.1, which is sequences. Okay, so if I ask you, what a sequence is, what would you tell me a sequence is? A series of patterns?
A pattern or a series of patterns.
A series of patterns? Anyone else got another definition? That's not wrong, I'm just... An algorithm? Okay. A sequence. All right, so look. Sequence is quite simply is a list of objects. That's all it is. It's a list of objects. In this class, at least to start off this chapter, it's going to be a list of numbers. But in general, it could be a list of functions, it could be a list of names of your friends, it could be a list of the people you hate. Whatever it is, it's just a list of something, all right? That's all it is. So objects is kind of very vague, isn't it? So let me give you some examples of sequences. An example of a sequence, and we are going to focus primarily right now on numbers only, all right? So here's a sequence of numbers. The way we write these out is we use a brace, because it's a list. We use a brace, and then we start putting in the numbers. So 1, 2, 3, 4, 5. There we go. I get real sloppy with the brace, okay? So, yeah. Okay, so there it is. There's a sequence of numbers, right? That is a sequence. Now, we refer to this as a finite sequence, and it's finite because it has how many pieces to it? It has 5 pieces, right? So there's 1, 2, 3, 4, 5. There's 5 things. That's a finite number. Done. Okay, so let's look at this. What if we have 1, 2, 3, but this time I don't want to stop ever. I just want to keep going forever. So what I'll do is I'll put dot, dot, dot. Normally in math it's 3 dots, but again, I get carried away sometimes. Sometimes I'll do 4 or 5. But normally 3 means carry that on. So from that 1, 2, 3, we should assume that the next one would be what? 4 and then 5 and then 6, and then, right from that? That would be an assumption though. But I think it's a safe assumption. This is called an infinite sequence. This is a finite sequence. Make sense? Okay. Now, when it comes to sequences, even though the definition is just that it's a list of objects, you can look at it from a more mathematical perspective that it's more like a function. All right, so let's try and look at a sequence as a function. A sequence as a function. All right. So to kind of motivate this, let's go back to our original kind of concept or notion of a function. So in the past, when we've written like f of x equals x squared, we all understand that's a parabola, right? And you plug numbers in, you square them and all that stuff. But if we go back to like even before, like when we were like first learning about functions, we could draw this like picture that would show like, okay, 0 goes to 0, right? If you plug in 1, you square it, you get 1. If you plug in 2, you square it, you get 4, right? If you plug in -1, you get 1, right? And this was kind of like a visual illustration of what's happening, right? Input, output, input, output, input, output. We could also plug in fractions, couldn't we? Because this is a real valued function. We can plug real numbers into this, right? Any real number. So I can plug in a half, and that would take it over to 1/4, right? Okay, over here, what I want us to look at is that we are looking at a sequence, that this is a list of the outputs. Okay, this is a list of outputs. Like over here, what is the list of outputs we have? 0, 1, 4, 1, 1/4, right? These are a list of outputs. But there's something special about these outputs. Because of the way they are listed, okay, so now consider this. Consider a function that takes in some number n. I'm not going to say x this time, and then it spits back to you n. What would this look like with that picture of input output? 1 goes to 1, 2 goes to 2, 3 goes to 3, and so on and so forth, right? And if I look at that list of outputs, 1, 2, 3, 4, that's basically this list right here, isn't it? But the kind of catch here is that I'm saying this is the function, but I'm telling you can only plug in certain numbers. Like I'm telling you, you're not allowed to plug in 1/2 anymore. You can't plug in 1 anymore. You can only plug in positive integers. That's why I changed my variable from x to n. Because when it's x, we all understand that can be any number, right? But if I change this to n, then there's kind of an understanding here that n is a positive integer. N is a positive integer. What are the positive integers? 1, 2, 3, 4, 5, 6, 7, right? So when it was x, it was a real number, right? So if it was x, it was a real number, we could say x belongs to that set, right? Do you all know the notation for positive integers? It's z. So what I'd say here is n is an element of a double struct z, kind of like a double struct r, but there's one little catch to it. You have to put a plus on the top right. That tells you positive integers. If you leave the plus off, it's all integers. And this is not important for this class. You don't need to know notation for the positive integers. It's just, why not? It's not that hard to see, right? Okay, so what I'm saying is this. If you were to I can erase this. If you were to compare the function x squared with the function n squared, visually, here's what we'd have. The function x squared would look like this. But if I tell you to now just look at the function f of n equals n squared, and I'm telling you that your n has to be a positive integer, what is the picture? Just the right side? Close. Just dots on the right side, right? Because you can only plug in positive integers. So I can plug in 1, can't I? I can plug in 1 and I would get 1. I could plug in 2 and I would get, well, you know, I changed it. Sorry, n squared. Sorry, that was my fault. I changed that. N squared would give you what? 4, right? If I went to 3 and then go to n squared, it would be up here at 9, right? So the red curve is what we studied in calculus, right? What we've been studying. That's a nice, continuous, smooth curve. We can differentiate it, right? Find the slopes of tangent lines. But it is a function defined on the whole number line. A sequence is a function defined on just the positive integers. You have an input. Your input is always going to start at 1, okay, and then go to 2, and then 3, and then 4. So let me try and kind of reconstruct this for you. As long as everyone's clear with this, the sequence is restricting the domain so that when you spit out the output, you're just getting dots along the curve instead of the actual curve. Okay, so let's go back to what I started with, which is this first sequence. And let's look at the infinite one. Okay. So does everyone agree that this is the output when I plug in 1? Right? This is the output when I plug in 2. This is the output when I plug in 3. If we're looking at it from the perspective of sequences are just outputs of a function that's restricted to the positive integers. So this is kind of like whatever my function is, and not this one anymore. This is like the value I'm getting at 1. This is the value I'm getting at 2 when I plug in 2. This is the value I'm getting at 3. Make sense? So this gets confusing because, like, when you look at these two notations, they're so similar, it's like, what's the difference? What is the difference? You tell me, what's the difference between these two notations?
One's integer, one's a curve.
One's an integer and the other one's a real number, right? And so sometimes people can like forget, okay, they draw this and they draw the parabola instead of the dots. So to get around that, so that you're not confused, what we're going to do is, anytime we're using sequences, we're not going to use the notation f of something. We're going to get rid of that notation. And we're going to use a different notation. The notation is this. Instead of using and saying that's the value that comes out of the function f at 1, we are going to write a sub 1. And then the next one is a sub 2, subscripted. This, a sub 3. So this number 1 is the output of this function when I plug 1 in. This number 2 is the output when I plug in 2. This is the output when I plug in 3. Right? So in general, for this particular sequence, you could say that this sequence is just the sequence a sub n. A sub n equals, I'm out of room. I'll do it out here. A sub n equals n. In other words, the input is the output. The input is the output. 1 goes in, right? 1 goes in, 1 comes out. 2 goes in, 2 comes out. 3 goes in, 3 comes out. Right? Okay, let me give you another example, and this I think will come to more light. Okay, how about this? God, that one's too bad. Okay, how about this one? 2, 4, 6, 8, dot, dot, dot. All right, that sequence, right, is a list of numbers. Those are the outputs. What I'm asking for you to consider right now is what is the function. Okay, so this is kind of like the f of n, right? That's really what I'm saying. What is the function that spits that out?
N times 2.
So, yeah, before we get too deep into this, here's what I'd like. I'd like for people to respond, but I'd like for you to raise your hand, because what's going to happen in this section, very quickly you're going to see, some people are going to get this, and some people aren't. Like, we're going to have light bulbs go off, and we're going to have light bulbs that never come on, all right? Like, it's going to happen. So I don't want the same people that know, like, see it answering. I want to have people that don't quite see it at least think a little bit about it, all right? So somebody want to tell me what the function is that would take, and I'll remind you, what this is saying is that when we plug in 1, it spits out 2. When we plug in 2, it spits out 4. When we plug in 3, it spits out 6, right? So who's got it? What do you got?
2n.
2n. Everyone agree? 2n? This is it, 2n. That is the sequence. That is the function that will spit out 2, 4, 6, 8, and it will keep going, right? Straightforward? This is the function, the sequence function, that will generate the even numbers, right? That generates the even numbers. Very important. It may seem trivial to you, but that's very important that you understand that. Okay, let's try another one. I'm going to give us sequences, and I want us to come up with formulas. All right, who's my next volunteer? I want the formula for this. What are those numbers? Odd numbers. What do you got? What? 2 plus n? What do y'all think? No, because if you plug in 1, you get 3, right? You always have to start with 1. In other words, when you look at these, this is a sub 1. That's what you get when you plug in 1. This is a sub 2. This is a sub 3. This is a sub 4. So when I plug 1 in, I need to get 1. When I plug in 2, I need to get 3. When I plug in 3, I need to get 5, and so on and so forth. You want to redo it? You see why it doesn't work, yes? Okay. Someone else? Go ahead. 2n minus 1. What do y'all think of that formula? Does that seem to work? Yeah, I think that's going to work. Now look, do y'all agree that 2n by itself are all the even numbers? So if you take that list right there and you subtract 1 from each number, you have the odds. Right? Okay. So that generates your odds, starting at 1. Isn't this fun? We're going to do another one now. I should just be pulling sticks. That's what I should be doing. Yeah, that's more fun. That's more fun for me. Let's see here. Erica. Yep, you're up. You're up. So look, we're here to learn, all right? So Erica, do you see at least some pattern in those numbers? What is the pattern? Plus 2 each time, which is like both of those lists, right? Is it more like this list or like this one? That one? Because they're even, right? So you can generate this list, right? Using this. But you don't want to start at 2. Where do you want to start? 10. So you need this list, but you need to add how much to that number? 8. And then if you add 8 to that one, where would you be? Right? And so 2n plus 8. That seem that bad? Got it? Hold a sec. Is that what you said?
So we have to think from 1.
Always, 1 is always the input.
Okay.
1 is always going to be where we start. So 1 in here gives you 10, then you plug in 2, you get 2 times 2 is 4, plus 8 gives you 12, right? Then 14. Heidi. Oh, yes.
Well, I know it's like the 2n minus 1, but I don't know how to get to the negative.
Okay, so it's like this list, because those are odds. But you don't want to start at 1, you want to start at close. 2n minus 1 gives you that, right? But you want that minus 6? Is that what you said? So what? Minus 7. Because you want this list, but then you want to take 6 away from each one of those. So you get 2n minus 7. Does it work? What happens if you plug in 1? Negative 5. Plug in 2. Right? It works? So that 2n is really nice because if I give you any list of odds or any list of evens, you can somehow use that 2n to kind of figure out where you need to start. Yeah? Okay, let's try another one. Yeah, this is fun. This is fun because I get to make them up. Okay, how about this? How about 5, 10, 15, 20? Don't blurt out the answer yet. Jordan. I don't think Jordan's here. Oh, there. I'm blinded. Jordan. What do you got going on here? This one is different, right? Because they're not jumping up. Each time it's not going up by 2. You have an idea? So when you looked at even numbers, they jumped up by 2, right? And we used 2n. When we looked at odds, we still used 2n because it jumped by 2, right? But we subtracted so we could shift it. 5n. Everyone want to see that? There's a common difference that we're jumping by in this, right? It's by 5 each time. So if we start out at 1, we get 5, then 2, 10, right? Luis, you all right?
Yeah.
Okay. I'm not sure what that smile is about. Just, oh. No. No, I'll wait till the real hard one. All right, you ready for the next one? Super important one right here. Super important one. I'm going to let you think about this for a minute, and then I'm going to call on somebody. The sequence is negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1. And you need a formula that when you plug in 1, you get what? When you plug in 1, you get what? Negative 1. And when you plug in 2, you get positive 1. And when you plug in 3, you get negative 1. And then so on and so forth, so on and so forth, so on and so forth. Luis. No, I'm kidding. David, you're up.
My first thought was n squared, but it's not. It's just going to make it positive every time.
Mm-hmm.
So it's if I plug in 1, and then if I plug in 2, if I plug in 3, if I plug in 4.
It's got to keep switching between positive and negative 1. No, it should switch from positive to negative 1 each time you do it.
But the sequence that the numbers you plug in are still 1, 2, 3,
1, 2,
5.
3, 4, 5. Yep. Y'all get it? I think we have it. So how many of you think you have it? Okay, we have a few that think they have it.